Okay, hi everyone. I hope you're all doing well despite the circumstances. The exams are still being graded by Alex and Maria, but hopefully we'll have your scores to you soon. I want to start today with lectures about F-element chemistry. So up till now, we've been focused on transition metals. And the next two lectures, including today, will cover lanthanides today and then actinides on Tuesday. And here we're dealing with, instead of d orbitals for the valence electrons, we're dealing with metal ions that have f electrons. So let me bring up the slides. Okay. This is really not a topic that's much covered in your textbook, so we've provided a chapter from an alternate inorganic chemistry book that does cover these elements in some detail. We won't go through everything contained here, but this is a good chapter for you to read. And so the elements that we're going to focus on are the ones highlighted in yellow here. And you can note that the first F series here, lanthanum through lutetium, is corresponding to the lanthanide series, and actinide, etc., is corresponding to the actinides. And for the lanthanides, these are also included or encompassed in a class of elements which is called the rare earth elements. So rare earth elements have similar chemical behaviors, and they tend to have 3+, as we'll see, for their common oxidation state, and be very ionic in their bonding. But the rare earth elements include the lanthanide elements, as well as scandium and yttrium, which are the sort of transition metal elements directly above them. So today we'll focus on these rare earth type elements. And these were initially discovered in Sweden in the late 1700s. And it was started by an army lieutenant, Carl Axel Arrhenius, who in 1787 found a heavy black rock in a quarry near the Swedish village of Ytterby. And Arrhenius was also a amateur chemist, or chemist on the side. And he thought that this was an unusual and possibly unknown mineral that might contain the recently discovered element tungsten. And so he thought this should be of interest to chemists, and he sent samples of the rock to various chemists for analysis. And in particular, Johan Gadolin at University of Abo identified a new oxide in one of those samples. And oxides are sometimes referred to as earths, because they come from the earth, of course. But Gadolin published his analysis of this new mineral in 1794, and it was ultimately named yttria and led to the realization of this new element, yttrium. And at a similar time, Syria was discovered and recognized to have a new element, cerium. And for many years, it was thought that each of these minerals had just one particular metal element, yttrium and cerium. But ultimately, it was shown that these are actually very complex mixtures of metals in the oxide lattice. And a variety of separation methods ultimately led to isolation of the entire lanthanide series. So a huge amount of discovery of elements stemmed from Arrhenius initially finding this heavy black rock. And all of the lanthanide series elements were discovered from these minerals and isolated from these minerals eventually, with the exception of one, which is promethium. So this is just showing the lanthanides stemming from Syria and the history of that. And so if we look at the rare earths here, you can see their abundances. And the term rare is perhaps a misnomer because many of them, particularly the early lanthanides, are actually quite abundant. And you can see that elements like neodymium have a similar abundance to cobalt in the Earth's crust. But as you proceed along, some of these get more and more scarce. And also there can be difficulties in mining these, particularly how do you separate the lanthanides from each other. But you'll note that promethium here is listed as essentially zero abundance in the Earth's crust. And that's not exactly true, that doesn't exist in nature. But the half-lives of promethium are actually all significantly shorter for all the isotopes, shorter than the age of the Earth, which is about 10 to the 9 years. And so that element is not found in yttria or Syria, together with all the other lanthanides as a result of it having decayed. And it was only in the 1900s, in the early 1900s, that it was even recognized that there was a member missing here for promethium from this series. And that led to then that was a puzzle, and it led to an extensive search to find this missing element throughout the early 1900s. And that culminated in 1947 when promethium-147 was ultimately separated from materials obtained at Oak Ridge from the fission of uranium. And so promethium does actually occur in nature, but it occurs as a decay product of naturally occurring uranium. And so it's in very small and even fleeting amounts. So promethium is particularly difficult to study, but all of the others are readily available. So we're going to think about how the electronic structure and properties of these lanthanides change as we move across the periodic table. In terms of sources, here are the minerals that provide the main sources for the lanthanides and other rare earth elements. And you can see what these consist of and where they're found. In actuality, modern production of purified lanthanides has come to be dominated by China. It used to be that the US had a lot of mining and production for lanthanides, but in the last decade or two, China has essentially taken over the production of these important elements in which are used throughout technology, and they've undercut the prices of other countries, and so that has led to a critical and urgent need for the U.S. and other countries to restart production of some lanthanides, ones that are deemed critical to technology. And so there is a lot of research, modern research supported, for example, by the Department of Energy on how we could more efficiently extract purified lanthanide elements of importance, for example, in magnets, or how we can readily recycle lanthanides after they've been used in a technology. So here are the lanthanides in terms of electronic configurations and common oxidation states. So you'll note here, this first column is for atomic electron configuration. And then when we oxidize and go to the most common oxidation state, which is lanthanide 3+, you see that all of the valence electrons are in f orbitals, right? So we can have 4f0 all the way through 4f14. And the 3+ oxidation states are by far the most common oxidation states encountered for lanthanides in compounds. And so if you have to guess an oxidation state for a lanthanide, you should always go with 3+. You'll note there are compounds and all of the 2+ lanthanides have been isolated. These tend to be rather unstable compounds with a couple of exceptions. But these are, in some cases, depending on the coordination environment, you also have a d electron. Instead of just having f electrons, as we go to these more reduced oxidation states, you can have a combination of f and d electrons. And then for 4+, there are occasionally instances where 4+ lanthanides are arising. And a lot of this has to do with the stability, the particular stability of lanthanides to an F0, where you have no F electrons, to an F7, where you have a half-filled set of F orbitals, and to F14, where you have a completely filled set of F orbitals. As we'll see, the lanthanides are essentially ionic in how they bond with surrounding ligands. And those electron configurations provide particular stability. And so that leads to, for example, a more frequent occurrence of these non-3+ oxidation states for cerium 4+, cerium 4+, which is F0, for europium 2+, which is F7, for terbium 4+, which is F7, and also for ytterbium 2+, which is F14. But for the most part, the compounds that we'll consider will have lanthanide in the 3+ oxidation state. And the other thing to point out is that if we look at the radii here, either for the atoms, but more obviously for the 3+ ions, where it's just F valence electrons, you can see this steady progression of decreasing radii for the lanthanide. And that's the usual trend that we see in moving from left to right across the periodic table, across a row in the periodic table. The size of an atom or ion will decrease. And that's because you're adding nuclear charge and the valence electrons in that same shell are not good at screening each other from that nuclear charge that's increasing. And so as you move across, you're getting a higher and higher effective nuclear charge and therefore a smaller radius. And so here's just a plot showing ionic radii and their steady decline, particularly for the 3+ ions as we move across from lanthanum to lutetium. Right? And so again, note 3+ is by far the most common oxidation state. And this steady decrease in ionic radius is known as the lanthanide contraction. But it's really just the same as our usual periodic trend in moving from left to right. It's just that here we have this very nice series of maintaining a common 3+ oxidation state as we do so. So I want to remind you of the F orbitals. So we've looked at these before earlier in the course, but there are 7 of them, and you can see their depictions here. They have 3 angular nodes, and you can see the M sub L values are decreasing from left to right as you get more and more Z character along an applied magnetic axis. Right, so ±3, these are the most squashed orbitals that spread the electrons out away from the Z-axis, and these have the highest orbital contributions to the moment. Really important for the reactivity and bonding of lanthanides is to recognize that their valence F electrons tend to be actually buried within the core electron density. So normally the core electrons don't participate in bonding. They're very contracted. They don't have overlap with the orbitals of surrounding atoms. And that leads to them just engaging in ionic bonds where charge interactions, positive metal cation and negative charge on a ligand or anion is leading to the structure. And so that's true for all of these 3+ lanthanides. You can see here the blue is showing the radial distribution function for the xenon core electrons for neodymium 3+, and the green, these are the this is the distribution for the 4f3, the 3,4f electrons. And yeah, they don't extend out as far as the core, meaning that they're essentially part of the core and won't engage in covalent orbital interactions. When you go to the actinides, on the right, you can see a comparison with uranium 3+, which is just below neodymium. And so now instead of 4f3, we've got 5f3 for the valence configuration. And in this case, because of that larger principal quantum number for 5f, we can now have some slight extension of the f orbitals past the core electron density. And that means actinide elements, depending very much on their oxidation state, have more of an interaction greater possibility of having covalent orbital interactions with their surrounding atoms and ligands. So I want to point out that I'm not necessarily seeing hands if you raise them. So if somebody has a question as we go through here, I think it's fine for you to just go ahead and speak up. Any questions so far? Okay. All right. So this is a really distinguishing feature, which you'll see in today lecture for today and Tuesday.
Are relativistic effects included in these maps?
Yes, and so relativistic effects are more prominent, of course, for the actinides because they're heavier. But yes, these get across a point. But taking into account relativistic effects, you'll see the same thing. Remember, relativistic effects will actually tend to expand the f orbitals, and so relatively speaking, between non-relativistic and relativistic, you'd expect even further extension of the f electrons. Okay, so just to summarize some of these points, for lanthanide 3+ metal ions, the valence 4f orbitals are buried within the core electron density, such that the bonding is mainly ionic in character. And that has other consequences for the spectral properties and magnetic properties of the lanthanides. So as a result, unlike the transition metals, lanthanide metals have extremely small ligand field splitting energies, right? Because these 4f orbitals don't have much overlap with ligand orbitals, the ligand field splitting or crystal field splitting energies are, instead of many thousands of wave numbers, they're only usually many tens or a few hundred wave numbers. And perhaps, as we'll see, getting up to 1,000 wave numbers. But much, an order of magnitude or even two smaller than usually observed for transition metals. And so all of these f orbitals are very close in energy. And so this has, as one consequence here, of course, vibrational modes don't as greatly affect the optical transitions for lanthanides, because moving those ligands doesn't really change the f electron energy. And so 4f absorption bands are extremely sharp compared to transition metal DD absorption bands. And so here you see some examples. These are absorption spectra for aqueous solutions containing praseodymium 3+ in its hydrated form at the top, and neodymium 3+ in its aquated form at the bottom. You can see these are at very long, well, you can see where these are in terms of wavelength. This is 380 nanometers to 580 nanometers. So they can, in these cases, be in the visible region. But note how sharp these are. These bands are spanning very narrow energy range compared to transition metal complexes. In terms of colors, you can see here, these are the colors of salts. These are all nitrate salts of the water 9, the 9 coordinate complexes of the lanthanide 3+ ions. And so these, of course, have the common structures for 9 coordination, which are some form of a square antiprism, capped square antiprism, or tricapped trigonal prism, or sometimes, depending on how they crystallize, somewhere in between. But you can see most of the colors are very pale, and some are completely colorless. The colors are most interesting here for praseodymium and neodymium. Those are the two that we just saw the spectra for. But there are faint colors here. As an additional consequence, because these f orbitals are all so close in energy, it's easy for the electrons to circulate between f orbitals. And that means that we generally don't quench orbital angular momentum for a lanthanide ion electron configuration. And so if you have f electron count that's other than f0, f7, or f14, then you can have essentially orbital degeneracy and circulating electrons that, as we saw earlier, lead to an orbital angular momentum. And with 7 orbitals to circulate between, the angular momenta here can be enormous. The orbital contributions can be enormous. And this is the reason that lanthanide ions are so important for magnets and magnetism. They can have very large moments with as many as 7 unpaired electrons, but also very large orbital contributions that can add to the moment, and large magnetic anisotropy as a result of that orbital contribution. And so that is what leads so orbital angular momentum is then what leads to coercivity in a hysteresis loop for a magnet. And so our best magnets often are involving lanthanides that have this large orbital contribution. And so just to take a step back, we can consider now the situation comparing a transition metal to a lanthanide metal. And so as we've seen throughout the course, these d orbitals, the 5 different d orbitals for a transition metal are split in the presence of a ligand field. And that splitting is usually 10,000 wave numbers or so, right? So this very large crystal field splitting, as we've seen, generally quenches orbital angular momentum for transition metals. And we usually then take and apply spin orbit coupling on a spin-only consideration of the electronic ground state to get a splitting of m sub s levels. And so the crystal field splitting is dominant here compared to the spin orbit coupling, which is small for the transition metals. For the lanthanides, the situation is reversed. The spin orbit coupling is actually generally much larger in energy than the splitting from the crystal field. And so in this case, we're going to have instead a spin orbit coupled ground state that we'll consider to be perturbed or split then further by the crystal field of the surrounding elements or atoms. And so this is entirely due to this contracted, buried within the core nature of the f orbitals in the lanthanides. Okay, so here's a look at the moments. We've looked at this before, but here you can see the for the common 3+ oxidation state, here are the colors. They're not so obvious from the image I showed you before in some cases. A lot of these are very pale with, again, the exceptions of praseodymium and neodymium. But you can see we're having very large moments possible here for these lanthanide ions compounds compared to the transition metals, right? And so that large moment contributes to the saturation magnetization possible in a magnet. So that's an advantage and counts toward the magnetic energy product. But also this large orbital contribution that gives the coercivity of a magnet and contributes to also to that energy product. All right, so because of their spin properties, there are a number of, and their electronic structure, there are a number of applications that lanthanides are very prominently used for. And we'll briefly touch on a few of those. So one that used to be quite common, and maybe less so now, is lanthanide complexes are used or can be used as what are called NMR shift reagents. And so, of course, as chemists, we very often use NMR spectroscopy to measure proton resonances for their relaxation of the nuclear moment. And that gives us a way of determining the structure and purity of an organic compound. For some of these organic molecules or even proteins that are very complicated, you get a very convoluted NMR spectrum where you have many overlapping peaks. And so one trick that you can do is to add in a lanthanide complex. So an example of a shift reagent is shown here. This is a europium-3 complex. And the idea is that in solution, the exchange of ligands and even proximity of the organic molecule with the lanthanide, you'll reach an equilibrium. And the spin and magnetic properties of the lanthanide will shift, that will impact the nuclear moment of the protons, and they do that through a through space effect, which is called a pseudo contact shift. But that magnetic moment of the lanthanide will cause the spectrum for the organic molecule to spread out. And so here are a couple of examples. And you can see that relative to a standard, depending on the shift reagent used, you can get quite different placements for these chemical shifts. But at the top, you see, the spectrum for N-hexanol in tetrachloromethane with this europium complex added. And you can see there's a much greater spread for these proton resonances, and you can get the splittings and intensity integration more easily. And then if you instead use, this is now, instead of N-hexanol, the lower spectrum is N-pentanol, also in tetrachloromethane. But this is using a praseodymium contrast agent. And this shifts to a different region of the chemical shift space. But again, the same idea. But you'll note that the direction that these are spreading out is even flipped here. And so there are rules about how these shifts will spread out, these peaks will spread out depending on the electronic structure of the lanthanide. And we won't go into those, but they're not too difficult to follow. All right, so this is a trick that could be useful for simplifying spectra for complicated organic molecules. These days, we tend to have quite large magnets associated with our interests, our instruments, and so a large magnetic field allows you to also spread out peaks in an NMR spectrum, and so this is a technique that's not as commonly used as it used to be. A related application, and very important application though, is using lanthanide complexes, particularly gadolinium 3+ complexes, as MRI contrast agents. And so here you see some complex multidentate ligands that were specifically designed to wrap around gadolinium 3+, right? And so you can see this DTPA BMA ligand here. You can see how it wraps around a gadolinium 3+ center and takes up all but one of the coordination sites. And so here to the right, you can see a coordinated water. And so the design here is that you'd rather not have free gadolinium in your body. It can be toxic, and some people have a strong allergy to it. And so you'd like to tie it up in a really strongly bound ligand that will eventually allow it to be excreted. But you do want also to have exchange site where water can come on and off of the metal. And as we saw, lanthanide ions are very labile, so these waters very rapidly exchange with surrounding water molecules. And so as they exchange, the spin of the gadolinium is increasing the relaxation rate, the T1, what's called the T1 relaxation for the protons of the water. And that allows us to have a larger contrast in imaging various tissues, depending on how readily their water content can exchange with the coordinated water. And so this is still quite a field of research. You want to have a very strong binding interaction of the ligand so that you don't have free gadolinium, but you also need to have accessible exchange of water. Another extremely common and important use of rare earths or lanthanides is as phosphors. And so many of you probably have seen minerals. If you go to a natural history museum, say the Smithsonian, you'll see these dark rooms where a lot of times lanthanide minerals are shown under UV lamps. And you can see this brilliant colored light being emitted. And so rare earth phosphors are used very commonly in lighting, producing lighting from a UV source. And that has to do with the particulars of their excited states and how when you excite from the ground state, you can create a excited state that gradually relaxes and emits radiation instead of thermally relaxing. And that in the right electronic structure, such as for neodymium 3+ here, you can also pump up and get population inversion and create a laser. So a very commonly used laser is the neodymium YAG laser, where you've doped neodymium 3+ into an yttrium aluminum garnet oxide solid. So we're going to finish today discussing a little bit about magnetic properties for lanthanides. that stem from electronic structure. And I think, as you've seen, one of the things I want to do in this class is to give you a chance to be exposed to some of the recent research in inorganic chemistry, and particularly transition metal and now lanthanide chemistry. And so for the rest of class today, we'll take a look at some interesting research topics that employ lanthanide ions and probe their magnetic properties. And you should don't be too concerned about following all the details of these research topics that get introduced. This is partly to inform you about some of the modern research directions and perhaps get some of you excited about research in those areas. So again, I want to point out, these two workhorse magnets that we use throughout technology. Samarium cobalt 5, remember this is cobalt, not carbon and 5 oxygens. This metal alloy of samarium and cobalt, as well as neodymium iron boride. These have enormous coercivities, large magnetization saturations, and therefore large magnetic energy products, making them vastly more useful than other magnetic materials. Right. And so what I want to discuss is the idea that lanthanides can also be incorporated into very interesting single molecule magnets. So we've already discussed single molecule magnets earlier in the course. Initially, the first single molecule magnet discovered was the manganese 12 cluster that you saw. And most of the initial examples of single molecule magnets were transition metal compounds. And it dominated the research in the area for a long time. But recently, lanthanide chemistry has completely taken over this area because it's been recognized that the electronic structures here can lead to much more spectacular magnetic behaviors. And this all started really about 17 years ago with a report from a Japanese lab. This is work from Ishikawa. And they studied the magnetic properties of this sandwich complex where you've got a terbium center. This is terbium 3+, and it's got two phthalocyanine ligands, so the blue atoms are nitrogen. And you can see there's a very nice square anti-prismatic coordination geometry for the terbium center. And each of these phthalocyanine ligands is has a 2- formal charge, so we have a total charge of 1-. But what Ishikawa and coworkers recognized was that this molecule shows slow magnetic relaxation. And they found that it showed slow magnetic relaxation. The probe they used is actually something called AC magnetic susceptibility. And this is the idea that you're probing the magnetism with a magnetic field that's switching directions at a very specific frequency. And as you vary the frequency and match the relaxation time for the moment in the molecule, you'll see a missing component from the measured susceptibility. That is the magnetic moment, if it has a barrier to relaxation where it's only slowly relaxing, it can't keep up with how fast you're switching the direction of the magnetic field. And so this leads to, don't worry about understanding the details of these plots of AC susceptibility, but this provides a way of directly measuring the relaxation barrier for the moment in one of these complexes. And so by this technique, they saw that there was very slow relaxation for this terbium complex. And it had a very large relaxation barrier compared to any of the transition metal compounds that had been studied. And so that was very exciting. What was not exciting was that this molecule, unlike manganese 12, it didn't show magnetic hysteresis. And that's because in a lot of these single metal ion complexes, tunneling through the relaxation barrier can be dominant. And so that's true of many, but as we'll see, not all single lanthanide ion complexes. And so here, they saw slow relaxation via the AC susceptibility measurement, but did not observe magnetic hysteresis even at very low temperatures. And that's because there are two mechanisms that play here. One is tunneling, which allows relaxation when you take away a magnetic field. All right, so just to understand a little bit about the electronic structure here. Each of these, so this is for a series now of those sandwich complexes between a lanthanide 3+ and two of these phthalocyanine ligands. And you can vary the lanthanide, of course, across the series. But what is being plotted here is the splitting of the M sub J levels associated with the spin orbit coupled J ground state, right? And so for terbium 3+, we have a J equals 6 ground state, and the M sub J levels associated with that, that's the various orientations of the magnetic moment with respect to a magnetic field, they split in this very unusual pattern. You can see very low in energy is the plus and minus 6 M sub J levels. And then there's a large energy gap, and you get to plus or minus 5, then 0, then 1, 2, 4, 3. And so this splitting is, again, it's occurring because of the impact of the crystal field or ligand field on the ground state. And so this splitting is dictated by the ligands surrounding the lanthanide ions and the specific positioning and electron donating properties at all of these sites on the square antiprism. And if you want to build a good magnet with a large magnetic anisotropy, it's all about achieving a very large separation between these large moment M sub J states and smaller moment M sub J states. And so this happens very nicely for terbium 3+. There's a few hundred wave numbers gap where you have this +6 up, say, direction for the moment, and down -6 direction for the moment, lowest in energy. And the selection rules require that you excite before you go from +6 to -6. Right? And so that's the energy barrier that is being created here and leading to this slow relaxation. And then you see here also some of the M sub J splittings for the J ground states of other lanthanide 3+ ions. So understanding why these splittings happen is about understanding the distribution of charge density in these various M sub J states. And so here you see a plot of the spatial distribution or angular part of the distribution as we go from low M sub J to higher M sub J. And so if we look, here's terbium 3+, right? And if you think about it, the positions of the negative charges on these ligands those are going to have a repulsive interaction with the F electrons of the terbium 3+. And if those F electrons have this sort of distribution, this squashed oblate distribution, then they'll best avoid the electrons of the nitrogen atoms in the ligands. And so that is why this M sub j plus or minus 6 is lower in energy than all of these more prolate distributions for the other M sub j levels, right? And so a similar thing occurs for dysprosium. For dysprosium 3+, this 13 halves, M sub j plus or minus 13 halves distribution best avoids those charges on the ligands. And that one is lowest in energy. So looking at these shapes, you can understand, to some degree, how this splitting is coming to be. And so that's a very simple sort of crystal field type model leading to these M sub j splittings for the spin orbit coupled J ground state. Questions on this? Okay, let's keep going. So it was only a couple of years ago that it was realized that these single lanthanide complexes could show magnetic hysteresis, indeed up to quite high temperatures. And the initial synthetic work was done by a graduate student, Conrad Goodwin, who was a graduate student in David Mills' group at University of Manchester. And he made the first dysprosocinium complex and showed that it was a really spectacular single molecule magnet. And so this paper has been uploaded to the B-Courses website, and I encourage you to give it a read. It's relatively short, but it's really about the synthesis and then magnetic properties, which were a spectacular step forward for the field of single molecule magnet research. Prior to this work, as they say, the largest activation barriers and hysteresis temperatures were, this isn't quite accurate, but on the order of 14 Kelvin. They were around 14 Kelvin, meaning you only saw magnetic hysteresis below about 14 Kelvin. But here they're showing that with this dysprosium complex, they can see magnetic hysteresis at temperatures up to 60 Kelvin. Right? And so that's a huge leap forward in terms of properties, magnetic properties. So here's the molecule. And what they did is they developed a way of using a silyl species to abstract a chloride. And the key was, if you have these rather bulky substituents on cyclopentadiene, two cyclopentadiene ligands, then they could support just having those two ligands on the metal, so long as the counter anion is not coordinating. And so this is a fluorinated aryl borate anion, which has a 1- charge and is not coordinating, and the solvent here also won't coordinate. So once you abstract the chloride, you could make this cationic form of this metallocene complex of dysprosium 3+. And you can see it has as shown, a bend in the structure. Right, so this is a really interesting molecule. Here's its crystal structure. And you can see, so these bulky T-butyl substituents are protecting the metal and keeping it from engaging with other ions, other species. And you have a relatively linear, almost linear coordination at the metal between the cyclopentadienyl ligands. And so here are just some magnetic hysteresis data showing that depending on how quickly they swept the field, they could see open loops up to as high as, I think in this case, 62 Kelvin. Of course, if you sweep quickly, then you can see hysteresis to higher temperatures. So that was an astounding result compared to previous single molecule magnets. I want you to also note that at zero field here in these hysteresis loops, there's a sudden dip. And that dip, where you're losing remnants, where you're losing polarization, that's due to tunneling. So these molecules still haven't gotten rid of that tunneling pathway that can ultimately lead to loss of polarization of the moment when you're at zero field. And so even though we're seeing large hysteresis, we're seeing hysteresis up to very high temperatures, well, relatively speaking for molecules, there is this competing tunneling, and that can shorten the utility time for the magnet. And so if possible, we'd like to get rid of that tunneling pathway for relaxation.
Can I ask a question?
Sure, please.
So you in the crystal structure, it's bent. How like repeatable is that angle? Like, is it more of just an ionic like type of steric repulsion that's leading to that bent nature, or like what is it?
Yeah, so yeah, essentially this is an ionic sort of interaction, right? Like all of the lanthanides, in this case, you've got the cyclopentadienyl minus ligands and the dysprosium 3+ ion, and this is sort of the best structure for maximizing opposite charge contacts. And if you vary the substituents on the CP ring, though, you can change. There are two parameters that are really important here: the bend angle and also the distance between the carbon and the metal. Right, the closer that is, the larger the M sub J splittings should be. And it turns out the more linear, the more axial the preference for the moment is. But you can tune this, so if you use exactly this cyclopentadienyl ligand, you always get this particular structure. But if you vary the bulky substituents here, you can adjust both of those parameters, the degree of bending away from linearity and the distance between the metal and the C5 ring of cyclopentadienyl. And those effects are very interesting. So this is just taken from magnetic data. This is showing how the relaxation times are varying with temperature. And this region here is where you're seeing thermal activation. You're at high temperature, you're thermally activating over the barrier. And that allows you to extract this activation barrier. So about 1,200 wave numbers in this really low coordinate lanthanide coordination geometry. We get a large splitting between the M sub J levels that gives us then this large activation barrier for the relaxation. And then at very low temperatures, you don't have enough thermal energy to go over that barrier. And the only relaxation pathway that you see then is tunneling. And so here, this is due to tunneling through the barrier. And so here's a little bit of a more detailed picture of what's happening. So for dysprosium 3+, we have a J equals 15 halves ground state in this case, M sub J ground state. sorry, J equals 15 halves spin orbit coupled ground state. And then these are the calculated M sub J splittings, right? And lowest in energy are plus and minus 15 halves. And then there's this large gap to 13 halves. And if you're going to go from the moment being up to down or down to up, you have to traverse this pathway, go over this activation barrier. And when you get up to here, mixing and tunneling becomes more probable. And so you can then go over this barrier and reverse polarity. But so long as you don't have thermal activation energy to get up above this 1,000 wave numbers or so, then you should maintain the direction of polarization. Right, so that's how these molecules operate as single molecule magnets. Okay, so that discovery has led to some even slight increases in the temperature at which these materials can operate, and blocking temperatures are now up just below liquid nitrogen temperature. And so these molecules can act as magnets up to nearly liquid nitrogen temperatures. But obviously we'd like to proceed to even much higher temperatures where we can see that magnetic hysteresis and potentially store information at a very small scale. Okay, so how do we get rid of tunneling as a pathway? One idea is that if you build a large magnetic moment, then the probability of tunneling through an activation barrier becomes smaller and eventually negligible. And so one idea is that you might try to couple spins or moments on multiple lanthanide centers. And that's hard to do because, as we said, the F electrons of the lanthanides are buried within the core electron density and don't like to engage with other orbitals, with ligand orbitals. And so lanthanide ions usually show extremely weak super exchange interactions. Right? Remember, super exchange means that the spin of the metal, the spin of the metal can interact with the spin of another metal by propagating through intervening non-magnetic atoms and orbitals. But the way to engage lanthanides in a somewhat stronger exchange interaction is to use direct exchange, where the lanthanide's spin can have a Heisenberg exchange directly with the spin of a ligand. So if we have an unpaired electrons on the ligand, that can have a strong interaction. And if that ligand bridges two or more lanthanide centers, then you can have a strongly coupled large moment for the ground state. Okay, and so that leads us to some really beautiful synthetic work by Bill Evans and his group at UC Irvine. And what they had done is they had shown that they could take this lanthanide 3+ complex and a strong reducing agent. This is potassium graphite. And under a nitrogen atmosphere, this would actually lead to activation and reduction of nitrogen and result in a bridged dilanthanide complex. And in this complex, the orange spheres here are lanthanide ions. And here you have on each end 2 amide anionic ligands, and then a THF neutral ligand. And overall, you have a 1- charge. And it turns out this N2 unit that's bridging between the two lanthanide centers is reduced to an N2 3- formal charge. So you've added 3 electrons to this triple bonded dinitrogen. You can also oxidize by 1 electron and isolate the the N2 bridged species. And so when they made these, they characterized particularly the cases where you have non-magnetic lanthanide ions. And so here, this is yttrium, which structurally is very much like a lanthanide ion, but has no, yttrium 3+ has no valence electrons. So it's going to be spin 0. And so you can see the structure here. This is the orbital that the unpaired electron of N2 3- resides in. So note that N2 3- is an odd number of electrons, and so it necessarily has an unpaired electron. And it is in this pi star orbital that you see here, which has delta type of symmetry with respect to the lanthanide metal ions on either side. And this is just an EPR spectrum showing that spin of the N2 3- bridging ligand is to some extent shared with the yttrium centers on either side. And you can tell that because these splittings here correspond to coupling of the nitrogen spin and yttrium spin, right? And so the important thing is that with N2 3-, that spin is in a very compact molecule, just 2 nitrogen atoms, and you have a huge negative charge, 3-. And that means that this pi star orbital is extremely diffuse. And the orbital character extends out significantly towards that lanthanide center and can even directly engage with orbitals on the lanthanide center. And so recognizing that, we decided that it'd be interesting to see how strong magnetic exchange could be for these types of complexes. And if you put gadolinium 3+ into that structure type, then you have a situation here. Gadolinium 3+ has a half-filled set of f orbitals, so it's F7. And that half-filled set of orbitals means that its orbital contributions are completely quenched. So it shows spin-only magnetism, and S equals 7/2 here. And so there's a large spin-only moment on each gadolinium. And it turns out that those engage in direct exchange, which is antiferromagnetic, with the unpaired electron on the N2 3- bridge. And so that gives us then a total spin of 13/2 for the ground state. And here we're just fitting the temperature dependence of the magnetic moment. And from that, we can extract this J value. Remember, these J values are, as we defined them before, for either Heisenberg exchange or super exchange. And the greater in magnitude they are, the larger the strength of the interaction. And so this was a huge increase over the largest previous exchange constants observed for gadolinium 3+, right? Going from -6 to -27 wave numbers. And what that means is that these exchange interactions will persist to much higher temperatures than in other molecules. And what's interesting about this molecule is that you can see here, it shows magnetic hysteresis up to about 14 Kelvin, right? And at that time, that was a record for the blocking temperature for a molecule. But you'll note that you don't see the same dips around zero field due to tunneling. And so tunneling is very much suppressed by the formation of this large moment ground state. And that allows you to see these very large open hysteresis loops with very large coercive fields. Here it's out past 3 Tesla. And if you strip away and make an even lower coordination number for the lanthanide centers, then you can get even wider hysteresis loops. And so this one shows, this molecule for the terbium complex shows hysteresis up to 20 Kelvin and even past if you sweep fast. But you also see at low temperatures, you see this really enormous coercive field. Oops. And so here we're seeing a coercive field of 7.5 Tesla. These are rivaling the very strongest magnets that we have. All right, so finally, we'll very briefly show you some research that is not yet published, but hopefully will be soon. And it's from a current graduate student in the department, Colin Gould. So Colin is finalizing or finishing up his PhD. He's writing up and doing final experiments now. But one of the many interesting things he did was he showed that you could get even stronger coupling between a lanthanide and a radical bridge by creating the first example of benzene 2-, which has a triplet ground state. And the way he did it was by designing this ligand. So this is a ligand that's designed to actually and predisposed to coordinate two lanthanides on either side of a benzene ring. And so he's going to react this new ligand he designed with two lanthanide ions. This is a crown ether that will coordinate the potassium. And this is a strong reducing agent, potassium graphite. And this all comes together to create this molecule shown here. And so here you can see, I think this is a better view, but you can see there in the center, there's a benzene ring, and the two green spheres are the gadolinium 3+ ions, and the nitrogen atoms are amido donor groups. And so you have this sort of tetrahedral coordination at the lanthanide on each side, but this ligand is forcing those lanthanides to come in close to that benzene ring. This is what's called an inverse sandwich complex. So normal sandwich complex, you have two flat aromatic ligands with a metal in the middle. Here you've got the flat aromatic in the middle and the metals on the outside. Right? And in this molecule, we already have a 1- reduced form of the benzene ring. Right? And that 1- benzene actually it has an unpaired electron, right? It's benzene 1- is spin 1/2. And the orbital of that benzene 1- species can again engage the lanthanide, in this case gadolinium 3+, with direct exchange interactions. And so here you can see you're getting to -28 wave numbers. So similar to the N2-3- bridge that we had in the previous example. What's really fascinating here, though, is if you use two equivalents of this reducing agent, then you can directly form the doubly reduced species, where now you have a second electron associated with this benzene ring. So benzene 2-, when you add two electrons to benzene, you're creating what we normally think of as an anti-aromatic species, right? So here are the frontier pi orbitals for benzene, and aromaticity with 4n+2 or 6 electrons gives us this nice stable form of the molecule. When you add 2 electrons, you're populating these anti-bonding levels, and these are degenerate for benzene, but this degeneracy leads to a strong driving force for distortion. And so usually if you try to create benzene 2-, the molecule will distort in some way to achieve a singlet ground state, an S equals 0 ground state. So this triplet will convert to a singlet because it distorts. And the beauty of this molecule, though, is that the way it's constructed, it's very constrained and it's very high energy to try to distort the benzene ring. And so this is for the first time a case where we can keep that benzene planar and symmetric and isolate then a triplet ground state form of benzene 2 minus. Right? And this is just showing you have even much stronger magnetic exchange coupling now between that benzene 2 minus triplet. As you increase negative charge, you should expect the orbitals are more diffuse and have larger overlap with the metal species. And so that's confirmed here. We have, this is now easily a record for gadolinium exchange coupling. But even more interesting, because it's a triplet, this leads to even a much larger separation between the spin ground state and the next spin excited state. Right? So this is on a relative scale. This is just comparing the various spin states. So lowest in spin is this case where you've got antiferromagnetic coupling, and with one unpaired electron, that gives you a 13 halves ground states. With the S equals 1 benzene, that gives you a S equals 6 ground state. But if you flipped one of these directions for the spin, you can then create an excited S equals half or S equals 1 state. And the point is, this separation is what you want to be large to make sure that you have a well-isolated high moment ground state. Okay, so I will leave it there, and we have a few minutes if anybody wants to ask a question. If you do, please speak up.
So this was like way back, but we were talking about which M sub j value is most stable, and we used like the 3D, like how it looked to kind of determine that. And there were some in which it wasn't the largest M sub j value that was most stable. Does that mean that then those kind of like barrier plots for magnetic hysteresis, that it would look more like a W than say
You mean, so for example, erbium 3 plus here, as I'm showing, has the plus or minus 1/2 lowest in energy compared to the higher M sub j? Is that the kind of thing you're asking about? Yeah.
Yeah. And then
yeah, go ahead.
There was a plot then further to the right, I think, that like shows it. I typically have only ever seen like these kind of like upside down V looking plots for energy barrier, but so that would look more like where the x-axis is like M sub j and the y-axis is energy.
Yeah, so you're referring to this, it would be inverted in this case. And what that means is that your lowest energy state is not polarized. So if plus or minus 1/2 is at the bottom and all the others are high, you can transition between plus or minus 1/2 and lose polarity, without this activation barrier. And so, yeah, it's critical to create a ligand field that has the splitting so that the higher moments, M sub j's, are lowest in energy. And indeed, for that, if you look at the shapes, if we go back and look at the shapes, yeah, this is a very good question. If we look at the shapes for erbium 3 plus, right, you can maybe understand this 1/2 best avoids those nitrogen ligands. That shape avoids it better than these others, and that's why it winds up at the bottom. If you wanted to make a erbium 3 plus into a single molecule magnet, what you'd want to do is try to have a ligand field that really avoids this sort of shape, one of these shapes, and makes those the ground state, right? Compared to these other shapes. Okay. Anybody else have a last question? All right. Yeah, go ahead.
I had a quick question. I think just a few slides before about the lanthanide-based single molecule magnet. Yeah. So you said, I might have misheard, but you said that this one does not show hysteresis?
That's right. Well, so it does not, it shows very strong tunneling such that you don't retain polarization at zero field. So you see the effect in this plot where at zero applied field, you see this sudden loss of moment.
Yeah.
In that terbium bisphthalacycline complex, it would go all the way to zero. So you might have some open hysteresis here, but when you get to zero, all of a sudden it can tunnel. There's degeneracy of those plus and minus levels, and you tunnel and lose polarity.
So then that one wouldn't be good.
It depends a little bit on what you want to do with it, but if your goal is to have it act like a magnet where you could, apply a field, line up its direction of moment, and then take away the field, yeah, the terbium complex that we looked at before would not be good.
Okay, thank you.
Sure. All right. Well, everybody have a good rest of your day, and we'll continue with actinide chemistry on Tuesday. And for this, we'll have a guest lecture from an expert in the field, Dr. Dominic Halter. All right. Bye, everyone.